Well, hello everybody, and welcome to lecture 10 of our Calculus 1 course. So today we're going to talk about the lengths of curves, also known as the rectification of curves. Finding the length of a curve is called rectifying it. And we're going to develop a formula, or we're going to find a formula for the length of a curve, and then we're also going to touch on a couple other topics, one called improper integrals, and another one, the other topic that we're going to touch on is approximation of integrals. So length of a curve. So here's the y-axis and x-axis for reference. And say that we have a curve over here. Let's call this point x0, f of x0, and we want to measure the length of the curve from x0, f of x0 up to some other point. So let's call this point, x, f of x. Then this length of the curve up to this point we'll call L of x. And okay, so we've called it L of x. We've named it, but it would be nice to be able to get our hands on it a little bit better. So right here, why I'm putting this in here will become evident as we go along. X plus h, f of x plus h. So here's another point on the curve. And if we approximate how L changes from this point to this point, we might be able to get the derivative of L. And if we could get the derivative of L, we could use the fundamental theorem of calculus to express L as an integral, and that's exactly what we're going to do. So this length right here, that length right there is L of x plus h minus L of x, right? That is what this length is. Now, that seems not really to help, but we can approximate the length by drawing a segment of a tangent line. And of course, this approximation, you can kind of see the tangent line is drifting away from the curve right here a little bit, but as h gets infinitely small, the tangent line will become an infinitely good approximation, and then the length of this tangent line will be an increasingly good and arbitrarily good approximation of the length of this segment. So let's compute this out. So the base of this, we can now have a right triangle now where this is the tangent line to the curve, a segment of the tangent line to the curve, and this length is h. So then this height, well, the slope is rise over run, right? So the height is going to be rise over run times run, right? The height is the rise, and the slope is f prime of x, right? Because this is the tangent line at x, f of x. So the slope is going to be f prime of x, and then the run is going to be h. So okay, so we have a right triangle with base h and height f prime of x times h. So this hypotenuse, which we're seeking, is going to have length h square root of h squared plus f prime of x times h squared. Can you see that? You can kind of see it. I'm going to write it again in a place that'll be more visible. So that says that this quantity right here is approximately equal to this. So this is approximately equal to square root of h squared plus f prime of x times h, this quantity in parentheses, squared. Okay, so I am going to erase this curve now in order to give us more space to, or this picture that's curved now to give us more space to manipulate this formula right here, but we're going to want to remember this picture and visit it. So then we can do the same trick we did before several lectures ago when we found the derivative of sine and cosine. And we can reverse engineer the linear approximation. So this we can factor out an h squared from inside of the square root. It's going to be h squared times 1 plus f prime of x squared. And then we can pull the h out of the square root. And so then what we can do is, so this all implies that L of x plus h minus L of x over h equals square root of, sorry, is approximately equal, the square root of 1 plus f prime of x squared. So taking the limit as h approaches 0, we get L prime of x equals the square root of 1 plus f prime of x squared. Because as h goes to 0, this approximation gets better and better, as I noted before on the picture. And so by the fundamental theorem of calculus, then what we're going to have is L of x equals the integral of the square root of 1 plus f prime of t squared, f prime of t squared dt. The top bound of integration is going to be x, and the bottom bound of integration is going to be x0. Remember, it starts at x0, and of course the length of the curve at x0 is going to be 0 because it's just at that point. And then as it moves along, the length is going to increase, and this integral expresses that we're going from x0 to x, and we're integrating L prime of x. This follows immediately from the fundamental theorem of calculus. We just integrate both sides of this equation. So that's the formula for the arc length of the curve. And let's do an example. I mentioned before that or did I mention that? I can't remember if I mentioned it or not, with the unit circle. So let's do it with the unit circle, and hopefully we'll get something that aligns with what we already know about the unit circle. And indeed, that is what's going to happen. I'm going to get something familiar, find another way of seeing something that we already knew. So, unit circle, or unit semicircle in our present case. This is 1, this is minus 1. Let's set x0 equal to 1. So this will be the length of the curve. Say this point is x and the square root of 1 minus x squared. so L of x is going to be the integral from 1 up to x of, say, f of x square root of 1 minus x squared of square root of 1 plus f prime of x squared dx. But then this expression right here is 1 plus, you can take the derivative of square root of 1 minus x squared, and if I'm going too fast with saying what the derivative is, you can pause and check it for yourself. It'd be good practice. But the derivative of this right here is going to be minus x over the square root of 1 minus x squared minus x over the square root of 1 minus x squared. Can you see that? Okay, yeah. And so this, we square this term, and we're going to want to get everything over a common denominator, but well, I'll start by just squaring the term. So here we get x squared over minus x squared, and then we want to get everything over the common denominator of 1 minus x squared. So this equals 1 minus x squared, turning 1 into 1 minus x squared over 1 minus x squared, right? So this is going to be 1 minus x squared plus x squared over 1 minus x squared. Of course, these two cancel. So this expression right here is just 1 over 1 minus x squared. And then, of course, that's underneath the square root bar right here. Okay? So I'm going to erase this stuff now and just put the square root of 1 minus x squared in place of the square root. So okay. And of course this, you can move the fraction, switch the order of taking fraction and square root. So this is going to be the integral from 1 up to x of 1 over the square root of 1 minus x squared dx. So we have an expression for the arc length. But remember, the arc length is supposed to be the angle, right? The angle is supposed to be the arc length of the unit circle. And of course, the x coordinate is of a point on the unit circle is cosine of theta. And so this length along here from x0 equals 1, this should just be theta, right? And theta expressed, I should be keeping better track of the variable of integration versus the bounds of integration. So this should be theta expressed in terms of x. And what's theta expressed in terms of x? Theta expressed in terms of cosine theta is none other than cosine inverse of theta. Well, is this cosine inverse of theta? Well, in fact it is. And the reason it is because of the fundamental theorem of calculus, this is going to be arc cos of x minus arc cos of 1. But arc cos of 1 is just 0, so it's just arc cos of x. So this function that we just integrated here, this function f of x equals 1 over the square root of 1 minus x squared. This function at 0 is 1, and then so over here this is negative 1, this is 1. It goes to infinity as x squared goes to 1, because then the denominator goes to 0. So as x goes to 1 or negative 1, it goes to infinity. And so we have asymptotes here. So something interesting, we know that this area right here is the integral from 1 up to 0 of 1 over the square root of 1 minus x squared dx, and that equals arc cosine of 0 minus arc cosine of 1. By the way, it seems a little bit weird that we're going from a bigger number to a smaller number, but there's really no reason not to do that if you think about it. This is, we established earlier that this integral is arc cosine. So, and that's again because arc cosine of 1 equals 0, and so this integral is arc cosine of the top thing in the bound. And so arc cosine of 0 is pi over 2. So this is interesting. This is interesting because what we have right here is an area which appears to be it's under a curve which goes to infinity. This curve goes to infinity as x approaches 1, and yet there's a finite area under this curve. And that's sort of strange, sort of peculiar, and sort of interesting. So this is a natural context where that comes up, where it's desirable to know this. There are more classical examples that seem to come out of nowhere but are simple to solve. So like, for example, a similar thing could be done with the curve y equals x to the minus 1/2. And this area right here, you know, this curve has an asymptote at x equals 0, and the area under the curve, so let's say this point is x equals 1. So the area under this curve between 0 and 1 is going to be integral from 0 to 1 of x to the minus 1/2 dx. And so remember, this goes to infinity as x goes to 1, of course, because this 1 over the square root of x goes to infinity, or sorry, as x goes to 0. This goes to infinity as x goes to 0. It's 1 over the square root of x. 1 over the square root of x as x goes to 0 goes to infinity. So the function's going to infinity, but its integral is not going to infinity, which we'll see here. Because if we just go along and act like everything's fine, it will be fine. Evaluated from 1, 0. So it's going to be 2 times x to the 1/2 evaluated from 1 to 0. And that's just going to be 2. So this area here is 2. Now, sometimes greater lengths are gone to speak of this in terms of limits, and I'll show you why that is. I'll show you why that is with another example. And let me go ahead and erase this. So, what about probably the first function most of us ever acquainted ourselves with that has asymptotes? I'm drawing those asymptotes a little bit too close. I'm going to try to fix that. Is the hyperbola y equals 1 over x. And I called it a hyperbola when we've been talking about a hyperbola as something else. It turns out this thing actually is a hyperbola, and maybe that'll be in some sort of exercise or extra credit problem at some point. I don't know. Maybe not. But this is a hyperbola. Anyways, side thought. But so, what about this area? We might think, well, maybe that'll have a finite area too, because we've been looking at these situations where there's an asymptote and there's an area contained in this asymptote, and it's a finite area. So we might think this would have a finite area. So let's try this out. Integral from 0 to 1 over x dx. So this is going to be log x, evaluated from 1, 0. This is going to be 0 is log of 1, right? So it's going to be equal log of 1 minus log of 0, which is going to be log of 1 is just 0. 0 minus log of 0 is minus infinity. And so this has an infinite area. Now technically, a lot of people don't really like, a lot of calculus textbook writers and calculus teachers don't really like this just throwing out infinity like that, just saying it's infinity. Maybe we should speak a little bit more carefully about it. So the way that they would insist that we speak is to say, well, because 1 over x is going to 0, let's slow down a little bit, and let's, instead of just calling it the integral, let's say limit as h approaches 0 of the integral from h up to 1 of 1 over x dx. And so then this is going to be the limit as h approaches 0 of log of 1 minus log of h. Then this equals limit, because log of h is just log of 1 is just 0, so this is going to be the limit as h approaches 0 of minus log of h. And this, of course, approaches infinity. And that way we're not being too assertive about infinity, which, for whatever reason, some people don't like to be too assertive about infinity. They consider it more rigorous to talk like this. But then, before returning to the rectification of curves, we're going to talk a little bit more about the rectification of curves. But before returning to that topic, I'm going to give one more example where, speaking of limits, is again a thing that is done. And this is the other type of improper integral. And it's the type of improper integral with a horizontal asymptote. So, say this is x equals 1, this curve is y equals 1 over x squared. So this area right here, we could write as integral from 1 up to infinity of 1 over x squared dx. So what this means might be self-evident, but we're going to write it with limit signs in order to be delicate around infinity, like I said, people tend to like to do. So let's say that this equals the limit as r approaches infinity of integral from 1 up to r of 1 over x squared dx. This, of course, is going to be the limit as r approaches infinity of negative 1 over, or I could write it really properly, so x to the minus 1 over minus 1, which is just negative x to the minus 1, evaluated from r to 1, well, x to the minus 1, so this is going to be limit r approaches infinity of 1 minus 1 over r. 1 minus 1 over r. I'm switching the signs from because of this negative. So we really have negative r to the minus 1 minus negative 1 to the minus 1, which is just negative 1, but double negative, so we end up with limit as r approaches infinity of 1 minus 1 over r. But 1 over r goes to 0 as r goes to infinity, so this equals 1. So this area is 1. And you can imagine this could also diverge. That's the terminology, is if this area is finite, it's called convergent. If this area is finite, it's called convergent. That applies to areas with vertical asymptotes as well. It's called convergent if the area is finite, and it's called divergent if the area is not finite. So, for example, so this integral, we say this integral converges because it's a finite value, but then an integral that diverges, like the example we did with 1 over x, diverges. But another quick example of an integral that diverges is if we consider this same function, but then try to take the integral over here, then the integral from 0 to 1 of x minus 2 dx, this is going to be the limit as h approaches 0 of integral from 0 to 1 of x minus 2 dx, and this is going to be, again, x to the minus 1 over minus 1, which from 1 to h, and then limit as h approaches 0. And then this is going to be, we can rewrite this as negative 1 over, sorry, I forgot the limit sign. I'll write it down here so we have more space. Can you see that? See that here? Yeah. So limit h approaches 0, of negative 1 over x, evaluated from 1, h. So evaluated at 1, it's just going to be negative 1, and then evaluated at h, it's going to be negative 1 over h as h goes to 0. It's going to be infinite. So diverges. So this integral diverges. So those are called improper integrals. So you have an improper integral whenever you're integrating near an asymptote. So you have integrating over a region that has either infinite height or infinite length. Yeah, so either a vertical asymptote or a horizontal asymptote. So okay, so let's go back to the rectification of curves, the length of a curve. So we did the example of the unit circle and everything worked out. We had a function that we're familiar with, arc cosine, and we had an explicit expression for the arc length, and that was really nice. But it turns out that's the exception rather than the rule. The vast majority of curves, you can't really come up with a nice expression for, and even other conic sections. So even the unit hyperbola, like a hyperbola or an ellipse, even these, finding the arc length, these are about as simple of curves you can think of, other than the unit circle and or circle in general. And even these, you can't get a good expression for the arc length. And we'll revisit what to do in that case in a minute. But first, let's look at a couple other special cases where we can get an explicit formula for the arc length. It's always nice to dwell on what we can do before we worry about what we can't do. So the integral that we're taking involves this expression 1 plus f prime of x squared. So let's think about some cases that we can deal with very well, where we can deal with this expression very well. And what they are is, what I have in mind is f prime of x equals tangent x, right? So if f prime of x equals tangent x, then we have the square root of 1 plus tangent x squared. So that's going to be, altogether, this is going to be secant. This is going to be square root of secant squared x. It's just going to be secant x. So that's going to be good. And the other example is quite analogous, and it is when f prime of x equals sinh x. If f prime of x equals sinh x, then this is just going to be the square root of 1 plus sinh squared x, which is just going to be the square root of cosh squared x, which is just going to be cosh x. And let's actually start with this example, because it is actually simpler. So I'm going to write up here, case A is f prime of x equals sinh x, and this can be accomplished by having f of x equals cosh x, and then case B is f prime of x equals tangent of x, and this can be accomplished by having f of x equals the natural log of secant of x. See, so that's why I said that case A is more simple, because f of x is just cosh x, as opposed to case B. Seems like, well, f prime of x is tangent x, like we're more familiar with tangent x, that would be simpler, but you get this weird thing, because it can be verified if you don't, we haven't done this in class, but it's easy to see, and you can stop right now and verify it if you want. It might be a good exercise that the derivative of ln of secant x is tangent x, which comes around pretty straightforwardly by the chain rule. Yeah, the chain rule. So, okay, so let's start with case A. Start with case A. So the integral, and by the way, I should draw the curve and say where we're gonna start from. So this curve right here, this is y equals cosh x. And so we're going to start from x equals 0 and find the arc length up to some point. So L of x equals the integral from 0 to x of the square root of 1 plus sinh squared t dt, which of course the reason we chose this example is that this is just cosh. This right here, this is cosh squared of t, so we just get integral 0 up to x of cosh t dt, and this is just going to be sinh x minus sinh 0, but sinh 0 is just 0. And so that tells us that the arc length along the curve y equals cosh x, starting from this point 0, is just sinh x. So that's pretty cool. That's something to contemplate. Very interesting. This is the relationship between cosh x and sinh x. It's that sinh x is the arc length along the curve y equals cosh x. I mean, in addition to the fact that they're also the coordinates of the hyperbola, this is another relationship between them, which is quite interesting. So let's go back to case B. So case A, check, done with that. Case B. So for case B, integral of, oh yeah, I should draw the curve and say where we're going to start from. So the curve looks something like this, very dramatic U-shape, sort of boxy U-shape that has f equals natural log of secant, because secant 0, sorry, secant 0 is 1, and ln of 1 is 0, so that's where we get this. And then for the asymptotes are where secant goes to infinity. So secant goes to infinity at minus pi over 2, right? Because that's where cosine goes to 0, and secant is 1 over cosine, and then pi over 2, so plus or minus pi over 2. So that's what the curve looks like, and we're going to start from 0. So we're going to find the length going along from 0 of this curve. And so it's just going to be the integral from 0 up, so this is L of x, equals the integral from 0 up to x of the square root of 1 plus f prime of x squared dx, sorry, t dt. Dummy variable is different than the bound of integration variable. So then this, of course, the reason we chose this example, right, is that this is going to be the square root of 1 plus tangent squared t, and this equals integral from 0 to x of secant t to t, which of course we know is the natural log of secant x plus tangent x minus the natural log of secant 0 plus tangent 0. But secant 0 is 1 and tangent 0 is 0, so this is just the natural log of 0, or sorry, the natural log of 1, which is 0, so this disappears. It's just the natural log of secant x plus tangent x, which is a quantity we've seen before. And yeah, so there's some hopefully optimistic examples of where we can find the arc length. And so another place where you can find the arc length, but it is a little bit more complicated, not too much more complicated, but is a little more complicated, is the case of a parabola. And I may make that some sort of homework assignment or assignment of some kind at some point, I'm not sure. But for now, let's go back to, I mentioned the ellipse, that for an ellipse that it is quite troublesome, and quite troublesome to find the arc length. And so say you have the ellipse 2x squared plus y squared equals 1. So this is an ellipse that has, sorry, 4x squared. The one I want to do this one, 4x squared plus y squared equals 1. So this is an ellipse that has semi-major axis 1 and semi-minor axis 1/2, right? This is 1/2, this is minus 1/2, this is 1, this is minus 1. If you forgot what semi-major and semi-minor axes are, it's not going to be essential for this conversation. So this is the ellipse, and let's say we want to measure the arc length from this point. So I'm going to leave it as a homework problem to derive the formula, but what it is integral from 1 up to a of the square root of 1 plus 12x squared over 1 minus 4x squared dx. And this expression right here is, sorry, I didn't specify what a is, and we could use I'm sorry, I changed the notation in my notes halfway through the process, so let's call this L of x so this turns out not to be an integral that we can evaluate and turn into a nice function. Now, in some sense, you could say, well, this integral just is itself, but of course, how would we evaluate it? And So we can represent this integral in a different way. We can represent it as the area under this curve. So of course it's going to be the same quantity. It still is the arc length, but we're instead going to represent it as the area under the curve. So we're switching representations of our quantities, but it's the same quantity. It's a beautiful thing we do in math all the time. So we could represent it as the area under the curve y equals, oh, another mistake I made. This should be going from 1/2, right? X equals 1/2, because at this point it's x equals 1/2. From what I said before, this should be x equals 1/2. But I'm actually now going to change it just because I'm going to say that we're going to start the arc length up here. So L of x is going to be this length. Okay, so L of x is going to be this length. And this highlight length. And so that changes this bound of integration to 0. Changes it to 0. Okay, so going back to changing this over to an area of a curve. So it's going to be the area under the curve y equals 1 plus 12x squared over 1 minus 4x squared. So in order to get an idea of what this curve looks like, I mean, we could think about it, but it could also help to graph it on Desmos and see what it looks like, which is what I ended up doing. But I'm going to reproduce to you what I saw when I did that, and it looks something like it has asymptotes right here. And it looks something like this. And what I'm going to propose to do is a approximation of the integral. So this is going to be the area. So this is, say right here, x equals 1/4. Then L of 1/4 is going to be this area right here. That area is L of 1/4. Now, we can approximate this area, and let me blow up this graph a little bit in order to depict what I want to say about approximating this area. So let's have this graph blown up. So right here we have, say, negative 1/4 and 1/4. So what we're going to do in order to approximate, steeper. In order to approximate L of 1/4, we're going to approximate this area, and we're going to do it by dividing it into little rectangles. Approximating it by little rectangles. So you can just see, looking at this picture, that the area under the curve here is approximately equal to the sum of the areas of these rectangles. So let's call these areas A1, A2, A3, and A4. Then, so L of 1/4 is approximately equal to A1 plus A2 plus A3 plus A4. And so if we divided this evenly from 0 to 1/4, this right here would be 1/4, or sorry, 1/16. This would be 2/16. I don't have enough space to write it, but this would be, yeah, I guess maybe I can. This is 3/16. And then, 1/4, of course, is the same as 4/16. And we've evaluated the function on the right end of the rectangle in each case. And so A1 equals f of space. A1 so we want the areas of A1, A2, A3, A4. So A1 equals f of 1/16 times 1/16, because f of 1/16 is the height of this rectangle, and 1/16 is the base of the rectangle. And so similarly, A2 equals f of 2/16 times 1/16. A3 equals f of 3/16 over 1/16, and A4 equals f of 4/16 over 1/16. And so now we can evaluate all these expressions. Just plug 1/16, 2/16, 3/16, 4/16 in for x in each of these places. And man, doing that by hand would be quite tedious and quite cumbersome, but what I've done is I've typed it into a computer, and I found that A1 equals 0.064, A2 equals 0.070, A3 equals 0.080, and A4 equals 0.095. And so when you add them all together, so this plus this plus this is approximately equal to 0.3106. And so your other homework problem is going to be to ask Wolfram Alpha to integrate this. I'll state the homework problems at the end of the lecture. But it'll be to ask Wolfram Alpha to integrate this and give an answer, and then to compare that answer to this answer and see how good of an estimate it is. So that's integration, approximate integration. And we could do this with any sort of function that we can't integrate explicitly, like, for example, sine of x squared, and that's the Fresnel integral, which some people found somewhere and tried to appeal to on a previous test. But the Fresnel integral could also be approximated in the same fashion with rectangles, and of course the approximation gets better and better the smaller the number of rectangles you have, as you could see in I think an earlier lecture I talked about that briefly, but Yeah. So a notational piece that I'll briefly mention here is, so we talk about integral of f of x dx. And I said that the integral symbol looks kind of like an S. It looks kind of like an S stands for sum. But a mathematical symbol that's used for summing things together, a way of saying sum things together, is this symbol, but this is a sigma, a capital sigma, a Greek letter, it's a capital sigma, and this is used to, sigma for sum. It's used to sum together a finite number of terms, or sum together terms. So like in the notation that's used, k equals 1 up to, or it's oftentimes n. It's oftentimes n equals 1 up to 4, say an. This expression right here, this is the same as a1 plus a2 plus a3 plus a4. It says take n equals 1, a1, then add this sigma, the sum means add together, so then add a2, then add a3, but then stop for n equals 4, so add a4, so this is a1 plus a2 plus a3 plus a4 is exactly what this is. And then if we look at these expressions right here, an is f of n over 16 times 1/16. And so you could call n over 16, you could call xn, and then, so this would be x1, this would be x2, this would be x3, this would be x4. So you could call n over 16, you could call it xn. Why not? Just call it xn. So 1/4 is x1, 2/4 is x2, 3/4 is x3, and 4/4 is x4. And then 1/16 is the difference between x1 and x2, and x2 and x3, and the difference between the two adjacent x's is 1/16. So we'll call 1/16 delta, this should be n, so this is xn, and this is delta xn. And so then you can see how this, if you take infinitely small subdivisions, so that the rectangles get smaller and smaller, the xn's get closer and closer together, and delta xn gets smaller and smaller. And this expression that's in Greek letters, with sigma and a delta, now this gets a Latin s, this is sort of the Latin s, this symbol for integral, and this delta gets replaced with a Latin d. And so I guess that was the thinking with Leibniz. Actually, that wasn't Leibniz's thinking. Leibniz was literally thinking of infinitely small rectangles being added together. But this is the motivation that's oftentimes given in calculus courses as to why this notation is acceptable, even though Leibniz's interpretation is not considered legit anymore. But so this is what I wanted to talk about today, and so to leave you off, let me give you your homework assignments. So homework assignment number 1. Homework assignment number 1, and this is worth 18 points. Homework assignment number 1 is to derive, so show work, derive an expression, because the answer is already given in the lecture, so the derivation is really what I'm asking for. Derive an expression for the arc length the arc length. So arc length is another word that's often used to describe the length of the curve. L of x for the curve y equals this is going to be this ellipse that I mentioned. The ellipse that I mentioned, which is 4x squared plus y squared equals 1. But I'm going to ask for the top branch of the ellipse, so it's going to be the arc length integral starting right here, going along. This is the point x0 equals 0 for the curve. So this curve is going to be the top branch of this curve, as I said. The top branch is going to be y equals the square root of, normally it's going to be plus or minus this, but we're going to consider the top branch square root of 1 minus 4x squared. So that's just going to be this top half right here, this curve. So derive an expression for the arc length L of x of the curve, I shouldn't say of the curve y equals the square root of 1 minus 4x from x0 equals 0. So, in other words, this is going to be integral from 0 to x of some expression, square root would be the square root of something, some expression that you'll derive, and then so derive an expression. So just derive an expression in terms of the integral. I'm not asking you to evaluate the expression explicitly, because I said that can't really be done within the scope of the functions that we talk about in this class. And what do I mean exactly by that? So your next assignment, sorry, this is going to be worth 15 points. So this is assignment 1. You probably want to screenshot it. Our homework problem 1. And then homework problem 2, worth 5 points. So this will be sort of an investigative, very, very, very easy problem to do, but we'll turn you loose a little bit. So go to Wolfram alpha. I know some of you are already familiar with Wolfram alpha, and some of you may not be. This was a traditional course where I was giving you lots of, if I gave this the same way that in-person delivery calculus courses are usually given, where you're just asked to compute a whole bunch of integrals, Wolfram alpha would be where you'd be going to cheat. You'd just type in the integrals and they'd evaluate them for you. So go to Wolfram alpha and do the following. Put the integral expression that I talked about earlier, which is the same one that you're going to derive for part 1. So go to Wolfram alpha and ask them to integrate from 0 to x of square root of 1 plus 12x squared over 1 minus 4x squared. I keep double using x. 1 plus 12t squared over 1 minus 4t squared dt. So ask them to integrate this, and the way that you do this in Wolfram Alpha language. So Wolfram Alpha uses a lot of AI, so they'll usually be pretty smart at figuring out what you're trying to say, but the sentence that you're going to type in is, and this is a quote. You can type this in word for word. Integrate SQRT. SQRT is a fairly common shorthand for square root. Is what Desmos also uses. So integrate square root, and then follow the parentheses in this way. They just want parentheses. Square root of 1 plus 12t squared, and then divided by is going to be this backslash. And I'm going to continue it on the next line, but it should all be in one line. You should write this all in one line. So 1 minus 4t squared, and then close parentheses. This closes this. This closes this. So this, you have this expression, you have this expression, this divided by this, and then you close these parentheses, then say from 0 to x. And Wolfram Alpha will understand you. And then what I want you to do, so that'll give you this integral, and kind of explore what they have to say about it. They'll give a bunch of sort of random facts about it and express it in terms of some functions called elliptic functions, which also relate to the arc length of ellipses that I mentioned. Unsurprisingly, also relate to the arc length of ellipses that I mentioned that we also couldn't integrate into functions that we're used to in this class. But so just explore that a little bit, and then the thing that you'll put on your homework that you turn in will be doing the same thing, only say the exact same sentence, only put 4 in place of x. So say the same sentence with 4 in place of x, and when you do that, you'll get a number, and compare the number you get to 0.3106, and say how far off it is from 0.3106, which is the number I gave for what this integral should be. So integrate from 0 to 4 now, and then say this integral is how far from 0.3106, the number I quoted earlier as the approximation that we get with the rectangles. So that's your homework assignment, and talk to you later.